Good day, my dear students. In today's lesson, we will talk about relationship among heat, work, and efficiency. Are you familiar with the game 4 picks one word? Can you guess the word? That's right, heat. Heat is actually defined as the energy transferred from one object to another due to their temperature difference. Now let's look at this scenario. If you accidentally touch a hot pot on your stove while cooking, you would involuntarily snatch your hand away from the pot. This response is called a reflex action. This special ability that evolution gifted us to facilitate our survival. Let's focus about the internal energy generated from a stove to the pot and later on flows to your hand. In this case, when you touch a hot pot, heat flows from the hot pot to your colder hand. The response of the nerve of the hand to the arrival of heat prompts your brain to identify the pot as hot. Remember that heat naturally flows from an object with higher temperature to an object with low temperature. Now let's guess another word. That's right, work. Work is defined as the energy transferred when an object is moved against force. Now, what is the relationship between heat and work? Let's look at this example. Heat engine is an engine which uses energy provided in the form of heat to do work and then exhausts the heat which cannot be used to do work. Heat engines move energy from a hot place to a cold place and divert some of that energy into mechanical energy. The most familiar example of a heat engine is the engine of a car, but most power plants like coal, natural gas, and nuclear are also heat engines. The concept of the conservation of energy states that energy cannot be created or destroyed. And the first law of thermodynamics is actually based on this concept. It states that the change in internal energy of a system equals the difference between the heat taken in by the system and the work done by the system. The law is expressed as delta U is equals to Q minus W, where Q is the amount of heat flowing into a system during a given process, W, the net work done with the system, and delta U, the change in the system's internal energy. This is derived from the conservation of energy given as how heat is related to work, or how heat is related to work, which is Q is equals to W plus delta U. Now let's answer some problem. If a 150 joules of energy is added to a system with no external work was done, by how much will the thermal energy of the system raise? Now for our given, we have Q is equals to 150 joules and our work is equals to 0. For what is asked in the problem, we have our change in the internal energy of the system. And to solve that, we need our solution, which is U is equals to Q minus W. And we simply substitute. And that would actually give us 150 joules. This is actually the change of the thermal energy in the system. As mentioned on the previous slide, heat naturally flows from higher temperature to lower temperature. But heat pump works the other way around. Heat pump is a device that allows heat to transfer from a cold reservoir to a warmer one, which cannot happen spontaneously or on its own. Work is required for the heat to flow from a lower to a higher temperature. This work is provided by the motor of heat pump. Now, how does heat pump work? For a simple heat pump, it has 4 basic components: condenser, expansion valve, evaporator, and compressor. In the heating mode, heat transfer from QC occurs the working fluid in the evaporator from the colder outer air, turning it into a gas. The electricity-driven compressor increases the temperature and pressure of the gas and forces it into the condenser. Condenser cools inside the heat space. Because the temperature of the gas is higher than the temperature in the room, heat transfer from the gas to the room occurs as the gas condenses to a liquid. The working fluid is then cooled as it flows back through an expansion valve to the outdoor evaporator hose. That is why heat pumps are usually used in houses, especially in colder places. Like your refrigerator, heat pumps use electricity to move heat from cold space to warm space, making the cool space cooler and the warm space warmer. They collect heat from the air, water, or ground outside your home and concentrate it for use inside. Now let's talk about thermal efficiency. Thermal efficiency defines as how well a machine operates. It is also the ratio of the useful work done to the heat provided. Applying conservation of energy, QH is equals to W plus QC. An important measure of a heat engine is its efficiency. How much of the input energy ends up doing useful work. The efficiency is calculated as a fraction, although it is stated as a percentage. Efficiency can be calculated as work done over input hit, or W over QH. Work is just the input hit minus the exhaust hit, so efficiency is equals to QH minus QC over QH equals to 1 minus QC over QH, where QC is the energy removed by the heat or energy in cold reservoir. QH is equals to the energy added by heat or energy in hot reservoir. TZ is equals to absolute temperature in cold reservoir, and TH is the absolute temperature in hot reservoir. Now let's solve a problem related to thermal efficiency. What is the efficiency of gasoline engines that receives 192.75 joules of energy from combustion and lost 125.25 joules by heat to exhaust during one cycle? For our given, we have our QC, or the energy removed by heat or energy in cold reservoir, is 125.25 joules. And our QH, which is the energy added by heat or energy in hot reservoir, we have 192.75 joules. Now what we're looking is the efficiency of that engine. And to solve that, our solution is 1 minus QC over QH times 100%. Now remember, we already have the necessary given to solve the problem. Let's substitute 1 minus 125.25 joules over 195.75 joules times 100. That would actually give us an efficiency of 0.36 or 36%. Overall, we can only have a 100% efficiency if there is no energy transferred away from the engine by heat. But in reality, there is no 100% efficient engine. There will be other losses to friction, for example, that will reduce the efficiency. That is why car manufacturers continuously create a more energy-efficient engine for lesser fuel consumption, because we all know that fuel is non-renewable energy. I hope you learned in today's lesson, my dear students. See you soon!